Hello, welcome everybody to a lecture on privacy in federated learning. Can you hear me and see my notebook? Yes, very good. So before I start discussing the the next coding assignment or quiz, which is necessary or required for the upcoming quiz, are there any questions from your side about anything related to the course? There was one question, now I remember, in the discussion forum about the requirements for the federated learning project. And remember that for each submission, for each report, you must submit also a Python notebook that can be run on our Jupyter Hub server. So you should try out your Python notebook, including all the numerical experiments for your project. You should run that on our Jupyter Hub server before submitting. We need to ensure this such that the reviewers, so which will be you, by the way, you will be the peer reviewers, that you have a chance to easily reproduce the numerical results that are used in the report. There's now one question. Is the grading over for all the quizzes? I haven't received the grade for one of them. Yeah, we just we are currently finalizing the grading of the last few quizzes. So maybe one of the notebooks, some of the notebooks are still to be graded, but yeah, I mean the quizzes are now still running. We will have 2 more quizzes. One of them I will introduce today. And another one has a deadline today, so they are still running and we are continuously grading them. So if you feel like we are lagging behind with your particular notebook, send us an email or ping us on Slack. But yeah, please take into account that we have quite some workload, so it might take a few weeks. So hopefully not too many weeks that you have all the grades, and at least till the end of the course, we should have everything in the grade book. Okay, any other questions? Yeah, now that we talk about the quiz, these last 2 quizzes, will be a bit more challenging in the sense that we do not provide you a starter code. We do not provide you a template notebook, but you have to start from scratch. So I will help you today a bit getting started with the dataset, but we do not provide template code now. This is now really testing your ability to solve a task by developing a small Python notebook. There's one question. Do you know, does Jupyter have some restrictions on the size? Yes, but I don't know the precise restrictions. So you should keep that in the mind that you might not use too large data sets. So if you use the FMI data, you should be fine, I would say. There's a question, will we have lab 3 with Raspberry Pi? No, there will be no more labs. I will use the resources, the teaching or course stuff resources now to support you with the project. In particular, we got already a request from some students who want to use a Raspberry Pi in the project. So we try to provide you these Raspberry Pis for the federated learning project. But there will be no lab 3 with Raspberry Pi. Okay, any other questions? Okay, if not, then I might now start talking about the next quiz, which comes with a coding assignment. In particular, the assignment is to develop a Python notebook that solves the exercise 11.2 in the lecture notes. So let me quickly share my lecture notes here. So we have exercise 11.2, and this exercise revolves around a toy data set, which is about diabetes patients. And you can find this and load this data set using the built-in functions of scikit-learn, or the functions of scikit-learn. So there's no challenge here to get the data, I assume. Yeah. The data points in this data set, or each data point, is a patient, and each data point is characterized by 10 features and a label that measures disease progression. So you don't need to know all the details about the meaning of these variables, just that we have several numeric features. In particular, we have a feature X2 and X3, which are blood serum measurements, which are labeled as S1 and S2. I don't know what that means exactly, this code. But we want to use these features X2 and X3 in our exercise. And there's another feature of a data point, which is the sex or the gender. It's a binary, has two possible values. And we consider this X1, this gender or sex variable, as the private information. So we would like to protect this the value of this feature as much as possible, as early as possible, in the machine learning or federated learning system. So as quickly as possible, when we read in the data, we want to somehow get rid of this X1 values. So we do not want to reveal this private feature. However, we still want to have features that allow to predict the quantity of interest, the label. So your task now in this exercise is to find a feature map that reads in the two features X2 and X3, which are these blood serum measurements, and delivers a new feature which is privacy preserving. So this new feature is denoted X prime, and this new feature should be such that it takes on at most 6 different values. So if you apply this feature map phi, if you apply to all the data points in this data set, in this toy data set, it should not take on more than 6 different values. Could be less than 6 different values, but at most 6 different values. So a bit more formally, this means that the new feature takes on values in a feature space of size 6. So again, it could be less. The new feature could take on fewer values than 6 different values for all the patients in the dataset. Yeah, please interrupt me anytime or ask questions on the chat. Okay, so this is the first requirement for this feature map. The second requirement is it should not be possible to find a hypothesis map that is applied to this new feature X prime and allows to predict the value of the private feature. So the new feature X prime should be such that you can never find a hypothesis map. You can be sure that there is no hypothesis map that allows to predict or guess the private feature value with a classification error smaller than 0.4. And we assume that this classification error is measured by the fraction of data points in the diabetes dataset, in this toy dataset, for which the prediction is wrong. So we do not compute expected loss, because we don't know what the underlying distribution is. Or in some sense, we assume that the underlying distribution is the empirical distribution of the data set we have. So the data set we have is basically the whole distribution of the data. So we measure this classification error by the fraction of data points in this toy data set that are classified wrong by a given hypothesis map. And yeah, we want to find the feature map such that the resulting new features are such that there's no way, you can never find such a hypothesis map that would allow to infer or predict the private feature X1 with a classification error strictly smaller than 0.4. So this is the privacy protection requirement, or the privacy protection that we want to have. However, I mean, the most trivial case would be, of course, we replace all data, we zero out all features. So we represent each data point in this database by the value 0. So by one single feature, which is equal to 0. So this would be perfectly privacy preserving. However, such a choice for the feature map, so this would be one possible feature map. It outputs always 0. Always yields value 0. But this would, of course, not allow to predict the label well. The label is this disease progression. So we still want to have some useful relevant information in this new feature X prime. In particular, we want to have this feature X prime such that there is at least one hypothesis map, so we can find or learn one hypothesis map that allows to predict the label with a relative average squared error loss strictly smaller than 0.2. And we measure the relative average squared error loss of a hypothesis using the squared error loss, average squared error loss divided by the average power or empirical power of the labels. So we sum the squares of the label values just to get a reasonable fraction or reasonable value range for this performance metric. Okay, so are there any questions at this point? These 3 requirements, we will then, the core staff, we will turn these 3 requirements into tests, you might call it unit tests, that we then apply to your notebooks. So we will then check, does this notebook contain code that produces a feature map such that these new features, when we apply the feature map to all the data points in the diabetes data set, such that these new features X prime have these properties. So at most 6 different values, could be less, does not allow to find any hypothesis map that can predict well the private feature, but does still allow to learn one hypothesis map that achieves a relative average squared error loss of not more than 0.2. Okay, so that's the goal, that's the task, and your submission for this quiz will be a notebook that contains code for solving this task. So for somehow the code should be able to produce or should allow to find out such a hypothesis map, such a feature map. So the hints here, there cannot be many hints because this is a fresh exercise. So this is really developed by myself, and it's I didn't see something similar anywhere else, including my lecture notes. So unfortunately, there are not many hints. I might leak out a few hints in the discussion in the Slack, and of course also via email for those who do not use Slack, but not at the moment. Okay, then yeah, I just want to walk about or show the data set. So here, can you see my notebook here? Thank you. So what you might want to do here is to, let me zoom in. You might want to load the diabetes data set. So where do we get the diabetes data set? Data sets. So it's included in data sets. And where do we? Oh, okay. Data sets. So here you can import data sets. Yeah, what I did then in this diabetes data set, you can read out the features, the raw features of each data point using the data attribute, and the label, the disease progression, is in this target attribute. So maybe let's organize this a bit more. So we move this below. So let's look at the raw data, the raw features. So let's have a look at what is the shape of this feature matrix. So we have 442 rows. This means we have a data set with 442 data points. And the raw features, there are 10 raw features. And you can orient yourself, so which feature is what, by using the feature names attribute. So feature names tells you what is the meaning of this. Let's say the first feature. What is the first feature? This is the age. So the age we do not use. We do not use at all in this exercise. The second feature is the sex. So this is the private feature. So this you could read out then, for example, in an NumPy array x1 as this private feature, and you read it out by diabetes data. These are the raw features, and then you select the first, the second column. So then you have it here. So now we have read out these sex values for each patient. So let's have a look how these values look like. So what is in this feature? And okay, now this is x1. I have already pre-processed it because in the raw form, these are just floating point numbers, but the important thing here is there are only two different values. So it's a binary variable. So it's then more useful to not use this looks like arbitrary numeric values, but the important thing is there are only two different numeric values. So it makes perfect sense to transform this to some more intuitive binary label set, which you could do with this label encoder, which is a nice tool. So you have a binary variable like the sex or the gender. So but somehow in the raw data set, this is encoded by two numbers. One is 0.05 and so on and so forth, and the other number is minus 0.044. So this is could be a bit suggestive that there's meaning in the numbers, and there's a meaning in this absolute value, but there is no meaning. So it's just either one of those two values. And to make this more intuitive as a binary variable, so I like to use this label encoder. So what the label encoder does, you fit the label encoder to the binary attribute, or here's this binary feature, and it then outputs you a natural representation using 0 for the first element, 1 for the second element, and so on and so forth. So if we apply this now here, we should get now print sex. This is now it didn't work. Okay, I print out one, and now I print out. Yeah, now I print out this transformed variable. So this variable sex is still nothing but x1, but it uses different numbers to represent the two possible values. Okay. Yeah, this might be convenient. You could also then use the same variable name. Say this is x1, So now you have transformed X private feature X1 in the alphabet. We could call it alphabet 01. Yeah, and okay, so this is the private feature. So we want to somehow transform the original features, which are, yeah, this I didn't tell you. We also need to get out this feature X2 and X3. So we need to find the raw feature, which is called S1. And this you could also look up in the user guide or the Python documentation. But I now tell you here. So this is, so now we print out too much stuff. Should be the fifth one. Yeah, the fifth raw feature is S1. And this is what we have in the exercise. It's called X2. So we read out diabetes data, the fifth column, and my educated guess is that the next one will be S2. Yes, the next one will be S2. So this is then diabetes.data 5. So these are the two features. The two features that describe a data point. And now your task is to somehow transform, combine, manipulate, or somehow map X2 and X3 to a new feature, X new, that allows to still predict well the label of a data point, this Y, but does not allow to predict too well the value of X1. Okay. So let's now have a look. I mean, we could now look at first, maybe just do a scatter plot of the data points using X2 and X3 as the coordinates and see how these original features could carry information about X1. So I have prepared this here. So I have searched for all the indices that have one value, 0 value for this private feature, and the other one which have value 1. And then I do a scatter plot first of all data points with value 0 for the private feature, and using X2 and X3 as coordinates, and then the same with the other value of the private feature. And we see here, so all the red dots are all the patients that have the same value for the private feature. So it seems that they are pretty much mixed up in the feature space, which is given by X2 and X3. But what do you think if I tell you X2 and X3? So let's put also here. So this is X2 and this is X3. So in this scatter plot, each dot here is one data point, is one patient, one diabetes patient. And I depict this patient using the feature value X2 and the feature value X3. And the color indicates the value of the private feature, so the gender or sex of the patient. So do you think, when you look at this scatter plot, if I tell you the value of X2 and X3, exactly the values, can you infer what the gender is of the person? So if I tell you, for this data point, I tell you the value of X2 and I tell you the value of X3, is there any other data point that has the same values for X2 and X3? Well, the thing is that if the entire universe or the entire possible choices of data points is exactly this data set, then knowing x2 and x3, as far as I can see from this scatter plot, identifies exactly a person or a patient, because there are no overlapping data points, except maybe one or two. They might be overlapping, but most of the data points, they are not overlapping. So each data point, each patient is uniquely identified by x2 and x3. So, and therefore you could infer the gender of the person, because you have the entire database and you have x2 and x3. So we could call x2 and x3 is something like an identifier, like a social security number. It's unique for each data point or for each patient in this database. So that's why using x2 and x3 directly might not be enough privacy protecting. Do you have another idea? So do you have a rough idea how we could map the values of x2 and x3 to a new value that somehow characterizes a data point, but not too much in the sense that it doesn't allow to tell if it's a red or a blue dot? I mean, can you think of any way to map the value of x2 and x3? Let's yeah, we could square it. This would be one way, square it. We could add an additional, well, that's basically the exercise. I require you to compress it. So I want to have one new feature, and then I only use this one new feature x prime to characterize a data point. So adding additional features is not allowed in this exercise. How could we combine somehow x2 and x3? What would be a trivial way to get one feature out of two features? Think of really simple solutions. Think very simple. Currently, we have two numbers that characterize a data point, x2 and x3. Take just one. Yes, take just one. Let's say we ignore x3. We ignore x3. So how could we realize this? How could we visualize this? We could just 0 x3 in the scatter plot to get a feeling how the data points then lie up. So we ignore x3, or we set it to 0. Identically, it's the same. So how does it look like? Okay, it looks like here. Can you be sure that yeah, we would need to zoom in more, but my educated guess is that still all data points have identified by the value x2. So again, it's too much information about the private feature in x2. So how could we reduce somehow the information in x2 about if it's a red or a blue dot? So we somehow want to make it indistinguishable if it's a red or a blue dot in the new feature space. Well, again, think very simple. How could we further transform or perturb x2? Yes, very good. There's an expert already here. Divide it into intervals, so quantize it, and replace the value x2 with the center of the interval into which this data point falls. So this quantization. And how many quantization intervals should we use for this specific exercise? We could use 4. Yeah, 4 would be allowed because it's less than 6. So from this exercise, we can use at most 6 quantization intervals, because the number of different values of the new feature must not be more than 6. Then, of course, the next question is, how should we choose the intervals? Should we choose them evenly or start from only 2? Yeah. And for this question, you now need to consider the requirements. So from the new feature, it should not be possible to classify or to predict the private feature with classification errors smaller than 0.4. So this somehow suggests that in each interval, in each quantization interval, it should be nicely mixed red and blue dots. So there should be not more, let's say, one dominant class with more than 60%. So this is one requirement on the quantization intervals. Okay. I mean, that's already some hints. The basic building blocks are now out there. I think this much I can tell. So the idea is to quantize, but maybe not in this. I mean, this approach I didn't try out. This would be one approach. Just ignore X3 and quantize X2. Yeah, it's up to you now that you see if this works, if this satisfies all requirements. I can only tell that I have found one solution that satisfies these requirements. So this I have found out. This I made sure there exists at least one feature map. Okay. Any questions regarding the exercise? There's a question, what about using the sigmas? I guess these are the variances of the distributions to divide into domains. Yes, you can do that. Yes. However, the ultimate goal, so the ultimate requirements are, it should not be possible from these quantized intervals or from these quantized features to predict the color, like blue or red here now, or the private feature. It indicates the private feature with error rates smaller than 0.4, but still be possible to predict the actual label with relative MSE not larger than 0.2. So we didn't take into account now in this discussion the actual label Y. This makes it, of course, interesting, because if we only aim after protecting privacy as much as possible, well, then you just delete all the data you have, or you zero it, or you don't release any data. Then you can never learn anything. You can never learn additional information about the private feature, because you don't release any data or only zeros. However, we want to release a bit of data in federated learning in particular. I mean, to put this into context of the federated learning applications. So in federated learning, we always need to share a bit of raw data. So this, for example, we could be the owner of this diabetes data set, and we want to support another researcher to learn something about the relation between S1 and S2 values and the disease progression. But we want not to share information about the gender or sex of the persons. So what we could do is, we could either use a federated learning algorithm, which doesn't share raw data at all. A federated learning algorithm only shares parameter updates of local models. Or we could also share raw data, but not the original features. What we would share is this transformed, this X prime feature, this new privacy preserving feature. This we could then share to our colleague, or with our colleague. Okay, so that's it from my side. I leave it now up to you. And next Wednesday, we will have a similar session, and we will just discuss a similar exercise, which is revolving around data poisoning. So instead of learning a privacy preserving feature in data poisoning, we do something else. We play a criminal, like an Austrian cyber criminal, who wants to mess up a bit this diabetes data set, such that the colleague that gets this poison data set thinks he has a good data set where he can learn a nice predictor of disease progression. But when he uses a standard learning algorithm to this, applies it to this poison data set, it has a very specific function. So the hypothesis that he or she will learn has a very abnormal behavior for certain feature values, which we know, which we as the poisoner know. And we could use this then, for example, to unlock a door to a lab. Yeah, so I will talk more about this then on in our lecture on Wednesday. Okay. Thanks a lot for your attention and have a nice evening. Bye.